Solve so many problems. I'm on a roll this season. This is flip string to monotone increasing. Okay, so let's go ahead and get right into this problem. So you're given a binary string S. Why am I reading it in that order? So a binary string is monotone increasing if it consists of some numbers of zeros, possibly none, followed by some number of ones, also possibly none. So you could think of that as just like a binary string, and that binary string is sorted, right? For example, if we took out this little pen and paper digitally, if we had 0, 0, 0, 1, 1, this would be monotone increasing because the zeros come before the ones. If we had 1, 1, 1, 1, 1, this would also be monotone increasing because we have possibly none. We have no zeros followed by ones. This, though, would not be monotone increasing because the 1 here is not in the correct place. Why? Because the 1 comes before the 0. And just like this said, the zeros have to come before the ones. So I guess the first observation, the most important thing you got to think about when you think about what it means to be a monotone increasing string is that all the zeros, all of them, all zeros have to come before all ones, right? That's always the case. All zeros before all ones. If that's the case, then you have a monotone increasing string. Okay, so in this problem, you're given a binary string S of ones and zeros, zeros and ones, and you can flip any of the bits, changing a bit that was 1 0 to a 1 and vice versa from a 1 to a 0. Return the minimum number of flips to make S monotone increasing. Okay, seems simple enough, right? Because you can take any string and you can just start flipping bits until you make it the case such that all the zeros come before all the ones. So for example, and we'll just do 1 or 2 examples here. If we had S equals 0, 0, 1, 1, 0. Note that this is not monotone increasing because all the zeros have to come before all the ones. Is that the case here? Well, no, because this 0 is causing an issue. This 0 doesn't come before all the ones. It comes after all the ones. So in order to fix this, what we could do is we could say, well, we're going to swap this 1 and turn that into a 1. And now you'll notice that 0, 0, 1, 1, 1 is monotone increasing. So we flip the last digit to get 0, 0, 1, 1, 1. So then we would return 1. Right? Because there's only one bit that we had to flip to make this happen. Okay, let's do another example. Let's say S equaled 0, 1, 0, 1, 1, 0. Well, it turns out in this example we have multiple options, right? Because obviously it's not monotone increasing because we have this 0 and this 0, which are causing issues. So one solution is we could just, we could turn this into a 1 and turn this into a 1. Right? And that would give us 0, 1, 1, 1, 1, which is monotone increasing. So that's 2 flips. But we could also, likewise, similarly, differently, distinctly, if we turned, what? Oh, okay, yeah. So we could turn this 1 into a 0 and this 0 into a 1. And that would give us 0, 0, 0, 1, 1, 1, which is 2 operations, 2 flips, and it's also monotone increasing. All right, and then the third example is more the same stuff. Right here, it would actually be optimal just to flip these 2 1s to 0s. You get all zeros, right? Because you don't have to have any 1s to the right. It's just that all the zeros have to come before all the 1s. If they're all zeros and it comes before nothing, right? There's nothing to the right of all the zeros, right? If these are all zeros, you can have possibly none, right? There could be no 1s to the right. Just if there exists a 1, it has to be on the right. That's the condition here. Okay, so how do we go about solving this problem? Well, I guess the most intuitive approach to kind of lead you to the solution, and we'll use this problem as an example, this second example as our solution, or maybe Yeah, we'll do the second one. It's always hard to know what's the best candidate to try to, develop a solution. And I think the second example is sufficient. So if we thought of this as a system of nodes, now, if you've watched any of my previous videos, you know that I love to model problems as graphs. I think that's the most intuitive and clear and descriptive approach. So just bear with me. But if we model this system as a graph, well, we have these nodes that we're going to traverse. So we have this node for 0, 1, 0, 1, 1, 1. I'm going to rewrite this just to give a little bit of space. So 0, 1, 0, 1, 1, 0. So 0, 1, 0, 1, 1, 0. So I'm just spacing it out, and it'll make sense why I'm doing this in a moment. Okay. Now, I'm going to group these nodes in a strange way, which will make sense in a second. So we have 0. I'm actually going to move this down. Sorry, I'm just doing some weird formatting things right now, which will make sense in a little bit. Okay. So this is the initial system, right? With our zeros and our ones. Now, the reason why I'm modeling it like this is because something that is a 0 can become a 1, right? And something that is a 1 can become a 0. So these aren't the only nodes that are in our system, right? We also have the flip side of these nodes, right? We have the situation where we don't use the 0 and we flip it to a 1. We take this 1, we flip it to a 0. We take this 0, we flip it to a 1. We take this 1, flip it to a 0. We take this 1, flip it to a 0. Take this 0, flip it to a 1. Right? What I'm basically trying to say is there's these blue nodes, which are the original vertices, right? The original nodes in the system as the system is given, right? This is what S was given as. But there's also these red nodes, which correspond to flipping bits, right? If we flip the bit, we get the red node. Now, we're trying to find the minimum number of flips to make S monotone increasing. So if we use a red node, right, that means we used a flip. And if we use a blue node, that means we haven't used a flip, right? So if I wanted to think of this in terms of edges, where edges have weights, well, if I use a blue node, right, for example, at this first instance, if I use the blue node, the cost is nothing. But if I use a red node, the cost is 1. Why? Because I had to flip the 0 to get to a 1. Now I'm going to play that same game going to everything, right? So from here, if I use this red node, the cost is 1. And if I use this blue node, the cost is 0. Now I'm going to, again, it's always formatting issues with me. So I'm going to go through everything really quickly. But just notice that if I use a red node, the cost is 1. If I use a blue node, the cost is 0. Why? Because in order to use a red node, that means I had to flip the corresponding bit, right? In order to get this to be 0, I had to flip this 1. But I'm going to quickly just draw out all of these edges links. So then we can think about this problem more clearly. All right, now every node can travel to any of the subsequent nodes if you flip. Or so it seems. Turns out that this problem is going to change just a little bit in a second when we think about the nature of what is actually possible, what is actually approachable, what is feasible. And then each of these nodes, right, if it goes into blue, it has cost 0. So I'll just set cost 0 to all the blue nodes. And if it goes into red, it has cost 1. So this goes into red. This goes into red, red 1, red 1, red 1, red 1, red 1. Okay. So I think I got everything, right? So if you use a red node, you have to spend 1 using that edge. If you use a blue node, you spend 0 because that's the edge that you're trying to get to. So really this problem becomes what? Well, it becomes finding the minimum path in this graph, right? I want to find the minimum path where I can use a 0 or I can use a 1 such that it's the minimum number of flips. But I guess the only additional constraint here is if we looked at this path and we said, okay, what's the minimum path, right? If we ran dynamic programming to find the minimum path in this graph, well, it would say, okay, 0, 0, 0, 0, 0, 0. There's a 0 path. Well, because that's just the initial string, right? The initial string is 0, 1, 0, 1, 1, 0. So why doesn't this work completely? Well, the issue is, right, is that I guess one thing you need to think about in this problem, which is our initial observation, all zeros have to come before all ones. So another way of stating that is as soon as I use a 1, I can't use a 0 again, right? As soon as I decide that I'm going to use a 1, either that be it's a 1 initially in the string or it's a flipped 1, right? When I make that decision, sorry, I have a runny nose. As soon as I make that decision, I can't go back and I can't use a 0 again, right? Because no 0 can be to the right of a 1. So as soon as I use a 1, I can't use a 0 again. So what that essentially means is that these edges don't actually exist, right? As soon as I decide to use a 1, I can never use a 0 again. Okay, so now does this capture the optimal solution? Well, I got 0 path here, 0 path here, a 1 path here, a 0, 0, and a 1. So what does this correspond to? Well, this corresponds to 0, 1, 1, 1, 1, 1, which is, okay, well, I've used this red one here and this red one here, so I must have flipped this bit and this bit. So using this graph will capture that information, right? Because in order for it to be monotone increasing, all the ones have to be the right. So as soon as I use a 1, I never have the opportunity to use a 0 again. So as soon as I decide to use one of these ones, either that be a 1 that's flipped or a 0 or a 1 that was initially a 1, right? Because this used to be a 0, so I flipped it to get a 1, or this was initially a 1. Either of those cases, as soon as I decide to use a 1, I can never use a 0 again. So that is completely encapsulated within this graph. So to kind of summarize what we did here to get to this graph drawn is we just thought about the system and the states, the fact that I can use an initial value or I can use its flipped. We thought about encapsulating or capturing the cost by making edges, which has a cost of 1 if you're going into a flipped 1, or a cost of 0 if you don't. So if we minimize that system, we'll get the minimum path with the minimum number of flips. And then we realized that since all the zeros have to be to the left, as soon as we use a 1, we can't use a 0 again, so we just removed the edges corresponding to using a 1, right? After you use a 1, you have no choice but to use a 1 subsequently. You don't have that option anymore. Okay. So what would be the recurrence relationship of this graph, of this DAG, right, this directed acyclic graph, to solve using dynamic programming? Well, let's say this is I here, right? So what's the best solution to get to here? Well, let's erase these green so it's a little... Right, when you run dynamic programming, you're basically asking, in order to use I here, what are the paths that I can take to get here? Well, I can use this path, or I can use this path, right? And then the cost of the edge corresponds to the node that you're at. So the dynamic programming solution, DP, for 1, right, 1 being these edges at the bottom, at I equals, well, I want the minimum path of, well, I can either, what am I doing? I can either take this path, which is DP, which is also DP of 1, but from the previous iteration, right? Or I can take DP of 0, right? Which is this one from the previous iteration. Hence the I minus 1. And then in order to get to this position, it's going to cost 1 if you flipped, and it's not going to cost 1 if you don't have to flip. So if I had to flip to get here, I can capture that by saying int the original string, which is S, at I not equal 1, right? So if it doesn't equal 1, then this will be a 1, right? So if it doesn't equal 1, then it's going to cost an additional 1 just to get here, right? Because that's the cost to get here. Otherwise, the cost is 0, right? Like in order to get here, the cost to get here using these edges are 0. So it would just be the minimum of whatever the cost is to get here, or the minimum of whatever cost it is to get here. So I take the minimum of both of these, and then this would be 0 because there's 0 cost to get to this node because I'm not flipping it. So if I flip it, there's an additional cost of 1, right? And if I don't flip it, there is no additional cost of 1. It's just the cost of the min of the 2 previous states. Okay? And then DP of 0, very similar. A little bit simpler, right? Because for any 0, right, like this 0, for example, I only have one previous state to check, right? So that means dp of 0 at I equals, well, I only have one state, so dp of 0 at I minus 1. And the same thing. If I had to flip the bit to get here, it's going to cost 1. So I'd say plus int si not equal 0 in this case, right? Because if it doesn't equal 0, we had to flip to get 0. Okay? So these are our two states. So we can just run through this whole system using dynamic programming and linear time. And then we'd have to create a DP array, which is of size n. But that could also be fixed because your state is only based on the previous state. So if I instead just called this 1, this would be 1 previous state, right? And if I called this 0, then this would just be 0 previous state. So then this would be 0. So then now my recurrence relationship is just two constant variables. It doesn't scale with n. I just say, well, 1 equals the min of 1 and 0 plus int of s of I not equal 1. And 0 equals 0, whatever 0 was before, plus int of s of I not equal 0. So now you have a very simple recurrence relationship based on this. And the reason why we can do this, right, is because you just update. If I is updated based on just I minus 1, you don't need to scale for everything, right? When I solve this recurrence relationship problem, I don't need information about all this. I just need information about the previous two iterations. Okay. So with that, let's go ahead and just solve it. So we'll just write the code really quick. Okay. So we'll say 0 and 1 equals 0 and 0. We'll look at each character in S, right? And then we'll update 0 and 1 using the recurrence relationship. We'll do it the other way because that's how I had it stated. So 1 and 0. So remember we said that 1 equals the minimum of 1 and 0. Let's move this up. Equals the minimum of 1 and 0 plus the int of the character not equal 1. Okay. So equals the min of 1 and 0 plus the int of the character not equaling 1. And then 0 equals what? 0 just equals 0 plus the character not equals 0. Okay. Zero plus the character not equaling 0. And at the end, we're going to have the optimal path to get to this state and to this state. So we'll just return the minimum, right? The minimum being if the last thing was 0 or 1, right? Because that could be, there's going to be multiple solutions to that part. So we'll just return the min of 1 and 0. All right. Get me nice and big over here. Let's take a look-see. All right, cool. So what's the run and the space? So let's say that n equals the length of n, or the length of s, sorry. And then for time, well, we just create these two constant operations. We have to look at all n characters in s, right? So we have to look at all n characters. Updating this is a constant operation. Updating this is a constant operation. So we look at n things, and for each n things, we do something constant. So constant times n, big O of n. All right. And then for space, well, we create these two variables, so that's constant. And then for each character in S, regardless of how big S is, we just keep updating these two variables. So if the size of Sn was 1,000,000 or 10 or 300,000 or 600 trillion, we would still only use these two variables when processing. So that would be big O of 1. Okay, guys. Hopefully you have a good rest of your day, good week. Merry Easter, Christmas, Thanksgiving, Hanukkah.